to Educate Foundation YouTube channel. Today we are going to look at the theory behind induced vertical stresses due to surface load. So remember that in our initial previous video, we looked at geostatic stress as a result of the materials. So for example, if I have this um, layers of soil, right? I have these layers of soil there without any material or without any load on top of the soil. So it's simply the soil. Now, if I want to know the force or the stress acting at this portion of the soil, it's as a result of the weight of material. So it's as a result of the weight of material above it. Here it is. It's as a result of the weight of material above it. So the weight of material is what is going to contribute or act at this point of the soil. So so at this particular point, the stress that will act at, let's say, this portion is as a result of the soil material here. Do you get it? Now, in that case, the geostatic stress, which we will call vertical stress, is as a result of the unit weight of the soil and the depth. Do you get it? Now, when I put a structure on the soil, now if I want, so assuming I have placed a structure on the soil, let me call this structure, the weight of this structure to be this thing in sigma. So this structure has its own weight, right? Now this weight that the structure has at the immediate surface that this structure is sitting on, the stress over there is going to be the stress as a result of the weight of this structure is going to be maximum. But the effect of the weight of this structure is going to what? Reduce. So it's going to reduce with depth. It's going to reduce with what? Depth. And that stress is what we call the what? Induced vertical stress. Induced vertical stress. So if you look at this structure, for instance, we have this soil, this is the groundwater surface, this is the water table. Now we are taking this point, can we call this point A? Now, assuming there was no structure here, the geostatic stress at point A is going to be the unit weight of what? Of the soil times its depth minus the unit weight of water times the depth of water to that point A. And that is the effective stress, obviously. Now, when this structure is down placed on the surface, on the on the soil, structure has a weight. You get it? And the weight of this structure will be supplied to the soil. Now, this weight that will be supplied, assuming it is the weight of the structure is, let's say, 10 kilonewton. At the ground surface, the whole weight or the whole soil is going to bear that weight. But as we move down, the weight will be decreasing because the impact of this weight of this structure will decrease with depth. So when we come to vertical stress increase. Vertical when it comes to vertical stress increase, it decreases with depth. Decreases with depth. You get it? But when we come to the geostatic stress, geostatic stress. So the stress as a result of sorry, geostatic stress, the stress as a result of what? Soil layer. For geostatic stress, it what? It increases with depth. Increases with depth. So let's take note of it. So in here we are looking at stresses in soil mass. So stresses in soil mass are due to either the geostatic stress then the additional stress. Now, when you put these two stresses together, so you get your total stress. So as we move on, we are going to look at the combination at a particular depth. We're going to find the geostatic stress. Then we are also going to find the additional stress, which we call the stress increase. And it's as a result of a structure placed on the soil. Do you get it? And so that is basically what we are going to look at. The next thing that we are going to look at is the methods. Now, it's easier for us to find it's easier for us to find the geostatic stress. Geostatic stress. Very easy. It's given by Tezagi's equation, that is the unit weight times the depth. Do you get it? And so if I want the effective is equal to the total minus or the pore water pressure. That's geostatic stress. But if I want the stress increase, the in the vertical the induced vertical stress. If I want the induced vertical stress as a result of surface load or as a result of a load placed on the soil, we have methods. So the method that we are going to talk about is the simplified 2:1 method. Now, in this method, what is simply is saying that, for example, you know that every structure, the weights of the structures are distributed, and eventually is the foundation that is going to bear the load, and the foundation is going to transmit the load to the soil. So if I have let's look at the simplified 2:1 method. In simple terms, if this is my foundation, right? If this is my foundation and the stress acts on the foundation, this foundation, the stress that's going to act on the foundation is going to be distributed in what we call the 2:1 direction. So the 2:1 means that in terms of direct vertical distance, it's going to increase in the ratio of 2. Then it's also going to increase in the lateral direction in the ratio of what? 1. So if I have, let's say, a heap of soil here, let's say a heap of soil here, and I place a plank on it and I press it down, realize that some of the soil is going to move in this direction and some of the soil is going to move in the vertical direction. So when the soil move in the lateral direction, that is the one, and it will move in the vertical direction as one. So we are seeing that it is assumed that the stresses is distributed evenly at a 2:1 distribution with this, meaning that when the stress is or acts is going to cause the soil to move downwards by a factor of 2, then laterally by a factor of what? 1. The other method that we are going to focus much in this topic is the elastic method. Very important. So we're going to look at each of the method, but our focus and most of our calculation is going to be on the elastic method. Now, the elastic method, we are going to use the Bosnick's and Westergaard equation. Westergaard equation. These are the two methods that we are going to use. Now, under the Bosnick, we are going to look at the point load. We are going to look at uniformly rectangular and foundation and the rest. So that is what we are going to focus. The finite element method, that one is more much of a computational analysis where we use software such as the Placid and um, most FEM methods or softwares. That one you use it for your analysis. So just as we said, so what we are trying to do here is that we want to find the vertical stress, vertical stress at any point in the soil. So if I have this soil layer, I'm coming. If I have this soil layer, for instance, I have this soil layer, right? Then we place a structure on the soil. Now the weight of the structure is, let's say, W. Then I want the vertical stress increase at this point. How do I go about it? Now, the vertical stress increases are simply the stress that is acting at this point as a result of this weight. Although at this point, there's going to be a geostatic stress, that is the stress as a result of the soil above or this point. There's also going to be a stress as a result of what? This structure on the soil at this point. And so that is the stress that we are looking for. And that is what we call the induced vertical stress or the stress increase. Do you get it? So we know that at this point, that stress increase is equal to the weight. But as we come down, that stress increase what is decreases. So how do I then find that stress increase here? Do you get it? All right. Now, in that method, we said that we can use the simplified 2:1. So this is a simplified 2:1 method. A simplified 2:1. So this is the equation for finding the simplified 2:1 method. So here we are looking at the stress increase at any depth. So this is a symbol for stress increase at any depth, and it's equal to Q. That is the force over the breadth or the width of the foundation times the depth that you are looking it from, multiplying the length of the foundation times the depth that you are looking for. Right? So assuming I have a foundation with dimension I have a foundation with dimension, let's say 2 meters by, let's say, 4 meters, right? And that foundation is acted upon by a force or the weight, for the weight of the structure, let's say, it's 20 kilonewton. And they are asking me to find the stress increase at a depth of, let's say, 4 meters. So in that case, my stress increase at a depth of 4 meters is simply equal to the 20 over what the width, which is 2, plus or the depth, which is 4, multiplying the length, which is 4, plus the depth, which is 4. Now, if you look at this very carefully, we are going to get 20 over what? 8, sorry, 6 times 8. So 6 times what? 8. And that's 20. So 20 over what? 48. And so that's going to give us 20 over, so let me check. So 20 over 48. Did I say 68? Sorry, 48. And that is what? 0.42 kilonewton per meter one square. So that is what the stress increase. Now, if the depth is, let's say, 1, the stress increase will increase. So at a greater depth, the stress increase reduces. That is what I was explaining here. Now, the next method that we are going to focus on is the elastic method. That is what I said that in this video or in this tutorial or in this course, we are going to focus much on the elastic method. But before we apply the elastic method, that is the Bosniak and Westergaard equation, we have to take some parameters. So the first parameter is that the soil that we are going to apply this method, the soil is semi-infinite. Semi-infinite means that when you are moving upwards, that is from the ground to the surface of the soil, it ends. But if you are moving from the surface of the soil downwards, because we are assuming that the soil does not end, and so that is, so in this case it is infinite as we are moving down with them. But if you are moving up from the soil bottom to the ground surface, it ends. So that is what we call a semi-infinite. So we are saying that this method can be used for any depth of soil. This can be method, the electric method, can be used for any depth of what? Of soil. You get it? So starting from the ground surface, 0 to what? Infinity. And that makes it what? An infinite, semi-infinite. If it is from infinity to infinity, then that becomes what? Infinite. But semi-infinite, it starts from somewhere and ends with somewhere. Do you get it? So that is the first component. So the soil is semi-infinite, that is elastic half space, and I've explained that. Then the soil behavior is linear and elastic, meaning that principle of superposition is applicable. So it simply means that if I have different layers of soil, let's say this is clay, this is sand, and this is gravels. If I have these layers of soil, then the stresses can be superimposed, meaning that the stress that will act here will act upon the stress that will act here. And these two stresses will act upon the stress that will act at this particular point. And that is what it means by what? Superimposition. We can impose the stresses on each other. Then also the soil is isotropic. The soil is isotropic. Simply means that the soil that we are going to consider, it has equal deformation in 3 dimensions. Do you get it? Mean that it this is 2 dimensions. So mean that the deformation in this direction and the deformation in this direction and the deformation in that direction all what equal. So that is the meaning of the soil is isotropic. Mean that in clay soil you only find only clay. You not find clay mixed with sand. No. So that is so the condition at which you apply the elastic method is what I'm giving to you. You cannot apply the elastic method when you have a mixture of, let's say, clay and sand in a soil layer. We cannot apply this, but we can apply it if each layer is distinct. So if it is a clay layer, it's only clay, if it's a sand layer, it's only sand, if it's gravels layer, it's only gravels. And in that case, if it's the same type of soil, then their deformation in 3 dimensional space will be what? Equal. Then the soil is homogeneous, and that is what I have just explained. So these are the conditions that we will look at in terms of the assumption. Now we'll move forward to look at the various methods or the 2 methods under the elastic method. We look at the Bosnick's method, then we also look at the Westergaard method. So in the next video, that's what we are going to look at.